Welcome back from the break. We are back at the headquarters, and yes, no need to adjust your screens. I am in black and white. It turns out imaging in black and white many times is better than in color. So in the next section, Nick will be demonstrating when to use either a color or monochrome camera, as well as how to use machine vision filters in different wavebands of light. So let's get back to the lab.
Hello everyone, and welcome back to the Edmund Optics Imaging Lab. I'm your host, Nick Sischka. In the first video, we talked all about telecentricity and how you'd want to use a telecentric lens if you're doing any sort of measurement or gauging application for your machine vision system. And now we want to shift gears a little bit more to talk about how you can manipulate wavelength and color through your system in order to maximize your precision within your imaging system. And so this is going to be applicable to telecentric systems and non-telecentric systems. Any imaging system is going to benefit from utilizing monochromatic or illumination, or just by changing and manipulating the wavelengths that are going through your system. So there's a few different ways that you can do that. You can utilize optical filters. In this particular case, this is a hard-coded filter that's actually passing blue light. You probably see it in the camera as having a yellow reflection, and that's because of the interference coatings that are on top of this. The other thing that you can, of course, do is take lights, and you can manipulate the wavelength of the lights. In this case, we can go to red or to blue, and that's probably what we're going to be doing over on the demo, just because it's easier than threading filters on and off, and it's going to give us the same effect. In a practical sense, when you're actually building a system, filters are useful because you can more finely control what's going on with the individual waveband. You can control the steepness of the curves, you can control the width of that band as well, in order to really finely tune what you need depending on your application. But color has really broad applicability in machine vision and in the things that it affects. And primarily today we're going to focus on three things that color impacts. It's going to impact our optical performance, it's going to impact our camera performance, and it's also going to impact our object performance, and we're going to refer to that here as object level contrast. So let's dig into each of these individually, and then of course we're going to pop over to the lab and take a look at how all these concepts translate in the real world under real conditions, looking at some objects. So we're going to start by talking about optical performance. So there's a couple different ways that color and waveband impacts your optical performance. The first that we want to talk about is called chromatic aberration. So I have a lens schematic drawn up here, again a very simple lens diagram, just like we've been showing before. This has an optical axis with a very simple lens here, and then what I've drawn is light coming into that lens from infinity, right? So we can see that these marginal rays in this case are coming into this lens from infinity, and I've drawn red, green, and blue right on top of each other. So that's kind of to simulate for you guys what white light would look like coming into this lens. And then you'll see that I'm focusing them at different positions. Right? And the reason that that's happening is because our index of refraction is actually going to vary depending upon the wavelength or the color of light that's coming into that lens. And we'll notice that blue is focusing closer, and then we have green, and then we have red focusing farther away. And so we're actually getting a change in focal length as we're changing the color of the light that's going through our lens. So that's going to impact our imaging performance with something that's called lateral chromatic aberration. It's axial chromatic aberration. And that's what's going on here. We're seeing this split in axis, and so we're seeing a defocus or a blur as we're changing the color of the light going through our lens. The next way that color impacts our resolution and our performance is via diffraction limited resolution. So we have an equation that's D equals 2.44 times wavelength times F number. And this D here is representative of a spot size. So you can imagine that if we have a lens and we're imaging an infinitely tiny object out at infinity, and it's coming into our lens and forming an image back here, the minimum sized spot that lens would form is represented by this D here. So we have this 2.44, which is a constant that comes from the derivation of this equation, and then we see that it is proportional to both wavelength and to F number. And so let's take a look at how this would look if we have two different wavelengths of light coming through our optical system. We're going to start with red light, and if we use a red light with our imaging system, we have a spot size of 2.44 times 0.66. I'm using that because it's a pretty common LED wavelength for a red light. And we're multiplying that by our F number, which I've set somewhat arbitrarily to f2.8, but f2.8 is a pretty common F number in machine vision systems. And so if we do that, what we wind up getting is a spot size, a theoretical spot size, of 4.5 microns. So that's going to be that size, that diameter of that spot that our lens is forming. Next, if we look at what's going to happen with blue light, We can take 2.44, multiply it by 0.47. Again, it's a pretty common LED wavelength there. And then multiply again by our f2.8 so that we're comparing apples to apples here. And what we wind up getting is a spot size of 3.2 microns. So that's a tremendous difference in terms of our size. It actually turns out to be an absolute difference there of about 40%. And that's going to create a huge boon to our optical performance if we can go with blue light. We're just going to get a boost in resolution coming from this diffraction, as well as we're eliminating the other wavelengths of light that are coming into our optical system, so we're just going to have to worry about one particular focus. So there's a couple different ways wavelength and color impacts our optics themselves, but it also impacts other portions of the system as well. Let's transition over to talking about how color can impact our camera performance. So here I have two different quantum efficiency curves. These quantum efficiency curves are for monochrome and for color cameras. This is a question that comes up often when we're doing machine vision applications or solving applications is, well, should I use a color camera for this? Especially if we're looking at sorting objects of different colors and things of that nature. The natural tendency for us as humans, who of course have color vision, is to use a color camera if we're trying to do something that's color sorting. But in fact, we're going to go over to the lab here and show how that's not necessarily the most advantageous thing to do in a machine vision sense. But here we have two different quantum efficiency curves, and the monochromatic system is basically going to view all wavelengths kind of on a continuum, right? And so we see that we have a response curve on our sensor that is going to vary differently depending on the wavelength. We see it peak somewhere around the green. I've put blue, green, and red marks here kind of somewhat arbitrarily, but they're not to scale or anything, but it's just kind of to show that we're maximizing our quantum efficiency or our conversion of photons to electrons on the sensor in that visible band, because we're looking at simulating a silicon camera here. And so we see that we're peaking around the green, but overall our performance in the visible is very continuous, and it starts to taper off in the IR and of course in the UV as well. The color camera as well looks a little bit differently, right? So here what we have actually is we have three somewhat more discrete responses to our wavelengths. And that's coming from the fact that here we have these Bayer pattern filters. So this Bayer pattern is actually over the top of each 2x2 set of pixels. So here we have two greens and one red and one blue pixel. So it's actually a filter that's over the top of each one of those pixels, and it's repeated throughout the entire array size. And so what we're doing is we're actually filtering the wavelengths of light that are making it to those individual pixels. We're going to show how that's going to impact our resolution and also just overall the way that the imaging system looks, because what it's going to do to regenerate that color is it's going to interpolate between where we're between the different colors and what we're actually outputting on the camera sensor itself for our image. The last thing that I want to focus on is our object level contrast, right? And so the type of light that you use has a huge impact on how your object's going to appear to your camera itself. And that's going to be one of the main things we're going to look at in the lab as well, is how does our object actually look? Because generally speaking, once you've taken an object and you pass it through a lens and you put it onto a camera and all that data gets recorded, each time you're actually going to lose contrast going through there. So the sharper you can have your object level contrast, the better your image is going to look overall. And so just quickly to define what contrast is for those who are not familiar, the equation for contrast is that you take an intensity, a maximum intensity, you subtract the minimum intensity between the two different things that you're trying to compare, and then you divide that by the sum of the same quantity, you multiply by 100 to get it into a percentage. And so just as a couple of quick examples for what it would look like if we're comparing the contrast between two different pixels, if we have all of our signal on one pixel and none of our signal on another pixel, we would have 100% contrast. It's generally not a good idea in any machine vision system to get 100% contrast, because it typically means that you're overexposed to some degree on your sensor, and that's what's going to show up as 100% contrast. 50% contrast means you have some of your information on one of your pixels and a little bit of information is bleeding over onto the adjacent pixel, and that's why we're seeing 50% contrast there. 0% contrast would be as if the pixels have the same value next to one another, and so you're not going to be able to tell any sort of difference between those two objects. So let's take all of these different things that we're talking about, from object level contrast to the camera performance to the optics. Let's head over to our lab and take a look at that. And one thing that I want you to remember just as we head over is we've talked about object level contrast here and how this is so important. But we've also mentioned here that typically we want to try to use small wavelengths for our optics performance. And we're going to see how sometimes these can be opposed to one another, but it's not necessarily the case, but it's important to think about both. So let's go head over to this lab and check it out. All right, so we're over here at the lab, and as usual, let's go ahead and see if we can put to practice some of the theory that we were talking about on the whiteboard. And we're going to want to talk about the same 3 different topics that we were just talking about over there. We want to talk about how we can manipulate our object level contrast. We want to talk about what's impacting our camera performance when it comes to the color and the waveband, and also, of course, what's impacting our optical performance as well. So let's take a look at each of those. Let's start with object level contrast. So what we want to talk about first is, of course, what our setup is here. And here we have 2 different lucid cameras. These cameras have the same sensor with a 3.45 micron pixel. The only difference is the camera on the left has one of those Bayer pattern filters over the top. It's a color camera, so it's going to output in color. And the camera that's on the right is outputting in monochrome. So that's the only difference there. And then they both have the same lens on them. It's an Edmund Optics UC series lens. They're both 25 millimeter focal lengths, and they're set to f4 for this experiment. And then the light that we're using is an RGB backlight from Metaphase Technologies. And so that's what we're going to be using to have everything set up and show you guys what's going on with color and waveband. The first thing that we want to take a look at is how we can manipulate our object level contrast. And what we're going to do for that is we're going to look at a couple different liquid gel capsules. You may be familiar with these. These are cold medicine, one that you'd take in the morning and one that you'd take at night. And you can see that they're different colors, right? One is green and the other one is like an orangish red color. And let's see how they're looking on the backlight here. So what we have set up is these 2 different setups here. The camera on the left, again, just to reiterate, is our color camera, and the camera that is on the right is our monochrome camera. And we can see right away that the pills look to our eye quite different with the color camera, right? Whereas with the monochrome camera, they look very similar, and that's because even though they're acting as bandpass filters, right? One is passing green and the other pill is passing red. They look very, very similar to the monochrome camera, so it's difficult to tell them apart. Meanwhile, on the color camera, it's pretty easy to do that. However, we're actually getting similar levels that are being pegged on the different pixels that are outputting the green versus the red. So even though to us it looks very, very different from an output perspective, they're actually quite similar if we were to compare those 2 levels. But what can we actually change and what can we manipulate in order to get our contrast levels looking different? Well, of course, we can utilize optical filters, right? We were talking earlier, we could pass these over the top. But instead of using the filters, I'm just going to change the color of the light because it'll be a little bit easier than threading the filters on and off as we step through the experiment. So first thing that I want to do is I want to minimize our red light, or we're going to maximize our red light that's coming through. We're going to go just to monochromatic. And as we can see, as this happens here, let's focus on our red channel here. We're seeing that immediately our green pill turns really, really dark. Right? And that's kind of exactly what we would want to see. It's kind of exactly what we'd expect to see, is that our green pill's turning really dark, our red pill is lighting right up. And on the monochrome camera, we can really see this as well. That the green pills basically look exactly the same on the monochrome camera versus the color camera. They're basically showing up as being black because they're not really letting any of that light through. On the monochrome camera, though, it would be really easy to set up a pixel threshold and basically binarize that. So you could have the red pills going through. Again, if we were trying to set up like a sorting application for these different pills, we could set up a threshold very, very simply with the monochrome system at a particular pixel value and just let that pass through. It's a little bit more complicated on the color camera because you're having to deal with those color channels there. And so what we've effectively done is we've manipulated our object level contrast to turn this into just a game of dark pixels and light pixels, and we can manipulate those values a lot easier on the monochrome camera and just have a simpler algorithm to work with. The other thing, of course, that we can do is do the opposite of this, which is to say we can use green light. So if we turn off our red channel, we turn up our green channel, here we can see that we basically get the opposite effect, where now our green pill is lighting up because it's passing that light wavelength through it, because light wavelengths pass light wavelengths on the color wheel. So green is passing green, and now our black appearing pill is actually the red one here. So that's what's going on when we're manipulating that object level contrast. And again, this isn't really a resolution problem, right? Both of these pills in this case are covering thousands of pixels. Neither the lens nor the camera is struggling to resolve these objects, but we can really get an idea here of what's going on between the contrast values of the objects that we're looking at. And contrast plays such an important role in machine vision to determining what we can and can't see, and that's really highlighted here. But let's take a look again about how it also can impact our color. So let me just balance this out really quickly on our white here. But give me 1 second to just balance this. It takes a second to manually do that, but I'll try to get it looking roughly white here. Manual color balance always takes a second. We're going to go with that there, though. So now we've kind of switched back on to white light, and now what we want to do is we want to take a look at a 1951 USAF target. So this is a negative USAF target, and if you watched any of our other summits, we've talked about USAF targets in a lot of detail. Basically what these targets are is they have alternating patterns of horizontal and vertical lines, and they're used to show the resolution of an optical system at really discrete values. And so as the target spirals inward, the resolution increases. So let's take a look at what happens when we look at that with a monochrome and a color camera. And we're going to look at what's called the Nyquist frequency here. And the Nyquist frequency in this particular case is going to be representative of exactly 1 pixel matching the width of one of these bars. And so then you'd have 1 pixel on the bar and 1 pixel in the dark part of the bar. And so that's like signal on, signal off. It's the bare minimum signal that you can use in a system without subpixel interpolation. So let's take these pills off here. Let's plop this USAF target on here. And let's go ahead and zoom in, give the camera a second to catch up. And let's zoom into what we want to pay attention to, which is, again, it is this group 3 element 1 here, which is right here. And I'll have to do some fine adjustment just to make sure that my target is actually aligned to what I want to see. And bear with me for 1 second as I do that. All right, it's about right there. Looks really good. And we'll do the same on the color camera here. And we're going to see some really interesting stuff as we zoom into the color camera. And we can automatically see that right now, where on the monochrome camera we're getting really good resolution still. I of course have to move that because, again, we're trying to line up exactly 1 pixel over the top of this object here. But you can clearly see the different features. And on the color camera, it just looks like a mess. And this is because what it's trying to do is it's looking at sharp whites and sharp blacks, and it's trying to interpolate and say, I know that this is white, but I don't have enough pixels to figure out what's going on. And so it's having a really hard time, and it's really struggling to interpolate that. And so what we can really see here is that we have a resolution loss coming from this color camera that we're not seeing on the monochrome camera because it's not having to try to figure out what color something is or is not. And so we're not getting this weird noise. And so we can see that even as I try to adjust this, all it's doing is really changing the colors that we're able to see coming into this system here. We're not really seeing anything different. It's not really showing up. But of course, one thing that we could do is we could come in here and actually change our color processing, and we can actually shut that color processing off, which I'll do right here. So I'm just going to go to no color processing here, and under white light, it looks like it improves our resolution. And so here we can now kind of move this. It looks a little bit more like a gingham pattern here, like a tablecloth type pattern. But one thing that you'll notice is that under this white light, we're not actually seeing consistent levels of color as we go through, or consistent levels of contrast from pixel to pixel as we go through. We can see this, like, kind of, again, that gingham pattern where we have bright pixels and darker pixels even on the same vertical line here on our target, which is of course non-ideal if we want to take a look at what's going on. And really, if we go to monochromatic systems, right, like let's say we want to use monochromatic system because we want to improve our optics resolution here, we want to get rid of that chromatic aberration that I was talking about, we want to increase our diffraction limited resolution by decreasing that spot size that we have. We can go back to a monochromatic wavelength, so let's say blue, because again, that's a nice low wavelength here. Now you can really see what's going on in terms of the color processing that was happening with white light. Where before, none of the interpolation was happening because I shut that off, and so it was actually able to just read the individual pixel values. Now we're only picking up the blue pixels because there you have the green and the red pixels with those different filters over the top. And so now we're only picking up a very discrete few pixels. We're picking up 25% of the pixels that we would normally pick up and see, and that's why we see this more accentuated checkerboard pattern here. And the same would happen if I switch to green light, right? And now it looks even more checkerboardy because here we have twice as many pixels, right? We have, from that Bayer pattern, we have 2 different green pixels in every quadrant of 4, and that's why it's showing up even more like a checkerboard. Meanwhile, our performance from our monochrome cameras basically been unaffected this entire time. We haven't really been seeing anything that's been stressing this, and we can even show that again by going to red light just to highlight that again. And again, we're getting really, really weird looking images coming out of the color camera. I don't know why you'd ever want to run a color camera like this. I'm in a practical sense, I just wanted to show everyone what's actually going on and how you're not really getting the benefit of the monochromatic illumination when you're going to that with a color camera. And so all of this is to say, like, when you're selecting a machine vision system, make sure that you're choosing your components carefully and try not to think about things the way that we see them. We tend to think about things in color because we view things in color, and often it can be a lot easier from an algorithm development perspective and from an overall machine vision perspective to think about things in terms of contrast. How can you turn color into brights and darks, and how can you minimize the features that you don't want to see while maximizing the features that you do, instead of having to rely on what colors look different, right? That can just make for an overall more reliable system, a faster system, and a system that runs more accurately. I've actually got one of our designers over on Zoom. They've been watching this the whole time. Let's get their opinion on wavelength and waveband and what they change when they're doing optical designs and how wavelength can impact their designs from an optical perspective. Thanks for watching.
Hey, Olivia, how's it going?
Hi, I'm good, thanks.
Awesome. Hey, how's Germany?
It's kind of chilly.
I guess you've started the descent into the dark winter of Europe, right?
Actually, the sun came out today. It was rather delightful.
That's amazing. That's more than I can say about New Jersey right now. So that's I guess I'm jealous. Never thought that I would be jealous of a late fall Europe. So nice. Wait, we didn't actually jump on to talk about the weather. So I wanted to kind of switch gears and kind of dive into what we just talked about in the lab, where we were talking about color and wavelength and impacts on systems. And I think the first thing that I wanted to ask you, right, is you do lots of designs and you start lots of designs, you finish lots of designs. But when you start those, when you're given a specification for a waveband or color, how much attention do you pay to how wide that waveband is, or what sort of things do you start thinking about when you see color specifications on a sheet that you have to design to?
It's basically one of the absolute first things we think about when we're setting up a system for a new design. You have to consider it because it defines a lot of your maximum performance that you can get, and also it will define all of the materials that you could possibly use, or if it's a kind of unique waveband or not necessarily like the common kind of like FBC waveband, so the red, green, blue that everyone recognizes. If it's not one of those, right, it could actually change, whether or not certain materials are available to you or coatings or things like that. So it's pretty much, I would say, maybe the first or second parameter that I think about when I'm doing my initial calculations for a design.
Okay, so you really pay attention to it up front. And then with respect to like materials, right? So are you saying that if you're designing a lens in, say, the ultraviolet wavelength range, you're going to choose different materials than if you were to design in the visible or in the IR?
Oh yeah, absolutely. And besides just like the very large distinct wave bands. I mean, even within, what we consider the visible, right? The 400 to 700, certain materials do better than others at the longer wavelengths versus the shorter wavelengths. And it can add a lot of cost ultimately. Is if you want a design that either has a very large waveband, you have to have materials that work across that range. Or if you have something that's a very specific waveband, it can really drive cost as well.
Mm-hmm. So does it increase, you talk about the materials, right? But it also increases cost, I guess. Do you need to use more elements when you do that type of design as well for a larger waveband?
Yeah, larger waveband is absolutely added complexity, and then therein drives cost. You generally kind of compensate for all the variations in color by adding more elements or needing more expensive materials that do cover that full range. It gets a lot harder the wider that band is, especially also if you consider like your field of view is also dependent upon that, because all of the different wavelengths, if you have a narrow band, right, they're going to focus differently, but within a region that's probably correctable. But if you have a huge waveband, right, you want to go all the way from the near UV to the near IR, you're going to have a huge spread in focus. So if you're at the best focus for, say your primary wavelength, the blur at those other two foci or the ends of the spectrum is going to be really large. And so the larger the field of view too, right, we have to take into account the angular extent, or how angles go through the system and affect that.
Wow. Okay. Yeah. So it seems like there's really a lot that kind of comes into play when you're doing those, when you're looking at the different wavebands and the different wavelengths and stuff. So if you're doing a really narrow band design, so like, let's say somebody's just using a green LED, can you just use a single glass material to do that? Or do you just use a narrower range of glasses?
You can just use a narrower range. There's advantage to having different materials in your system, not just necessarily for color correction, but also for other correction as well. Okay, perfect. So they can do kind of double duty, those different materials. Awesome. So I think we talked about materials a little bit, but like what sort of things when you're actually doing the design, what sort of tools do you have at your disposal in order to mitigate the effects of wide wave bands or of white light going through a lens? Glass is really the primary one. Mm-hmm. The number of elements is also another one. And if you think about, putting elements next to each other and creating like a different boundary, a different material boundary. So this is what we're talking about with like doublets or triplets or acromats. That can also change the effects throughout the system. Very cool. For color, really primarily it's materials. Mm-hmm. So basically, and that's also, I guess, not just glass, it's also coatings.
Okay, so do you pay more attention up front to the glass, or do you kind of look at coatings and glass at the same time, or?
I think generally up front, I spend more time wanting to make sure that the glass itself operates well within the specs of the system before then adding coatings. Typically coatings is, it's a kind of secondary way to mitigate color effects, because you're talking about more the illumination and like transmission necessarily in coatings than the actual like aberrations that come out of color effects.
Got it. Okay. So I guess as kind of a final fun question then, I guess, would you, is it more fun to design narrow waveband lenses or more fun to design challenging, like really wide band stuff?
I don't think that there's a one yes or no to that question. I think every design is challenging and therein fun in its own way. I mean, I've had just as much fun designing a monochromatic system as I have doing one that had two separate wavebands. So
maybe we'll have to start doing microlithography lenses at some point. That would be fun, right? Talk about narrow band. Awesome. Well, hey, Olivia, thank you so much for sitting down with me and having the chat. It's been super valuable, and I really appreciate your time.